Somewhere in the depths of space, roughly 900 million light years from where you are sitting right now, there is an object that should not exist according to a law of physics that scientists have trusted for over half a century. It is a black hole, but it is not behaving like one. It is not sitting quietly at the center of its galaxy, feeding slowly, predictably, the way every model of black hole growth says it should. It is doing something that, by the mathematics we have relied on since the 1970s, is supposed to be physically impossible. And NASA's own instruments confirmed it, not once, repeatedly. This is not a glitch in the data. This is a black hole that has apparently been ignoring the speed limit of its own growth for millions of years, and nobody currently has a clean explanation for how. Here is the number that started the entire investigation. There is a theoretical ceiling on how fast a black hole is allowed to consume matter, called the Eddington limit, named after the astrophysicist who first worked out the physics behind it more than 100 years ago. It is not a soft guideline. It is a hard physical boundary built from basic radiation pressure, the outward push of light and energy generated as matter falls into a black hole, fighting against the inward pull of gravity trying to drag more matter in, cross that boundary, and the radiation pressure should become so intense that it blows the incoming material away before the black hole can swallow it. It is physics acting as its own safety valve. For decades, this limit has been one of the most dependable rules in all of astrophysics, and the object NASA has been studying appears to have been feeding at more than 40 times that limit, sustained not for a brief flash, but for an extended stretch of cosmic time. I am your name, and this is your channel. Subscribe now if you want more stories like this, because we are just getting started. To understand why this is such a serious problem, you need to understand what the Eddington limit actually protects, because it is not just an abstract number sitting in a textbook. It is the thing that determines how fast any black hole in the universe is allowed to grow. Picture a black hole surrounded by a swirling disk of superheated gas. The material it is actively pulling in and consuming, called an accretion disk. As that gas spirals inward, it gets compressed, heats up to millions of degrees, and radiates enormous amounts of energy, mostly in the form of intense light and X-rays. That radiation pushes outward, directly opposing the gravitational pull dragging the material inward. For most of a black hole's life, gravity wins comfortably, and matter falls in at a steady, sustainable pace. But if a black hole tries to feed too fast, if too much matter tries to funnel in at once, the radiation being generated becomes so powerful that it starts physically blasting incoming material back out before it can ever cross the event horizon. The black hole essentially chokes on its own light. This is the Eddington limit in action, and it puts a hard ceiling on how quickly any black hole, no matter how large or how hungry, is allowed to grow. This ceiling matters enormously because it directly shapes one of the biggest open questions in modern astronomy. How do supermassive black holes, the kind that sit at the centers of galaxies and weigh millions or even billions of times the mass of our sun, get so big in the first place? If black holes are only ever allowed to feed at or below the Eddington limit, then building a supermassive black hole takes an extraordinarily long time. Hundreds of millions or even billions of years of steady, rule-abiding growth. That timeline works reasonably well for black holes we observe in the relatively nearby, and therefore relatively recent, universe. But it runs into serious trouble the further back in cosmic time astronomers look, because telescopes have already found supermassive black holes that appear to have reached staggering sizes far earlier in the universe's history than the standard feeding rate should allow. It is one of the most persistent puzzles in cosmology. How did the universe build black holes that massive that quickly, if the rulebook says growth has a strict speed limit? That is the exact question this new discovery slams directly into, because the object NASA has been observing is not just bending the Eddington limit slightly, it is blowing past it by a factor that, until recently, most astrophysicists would have confidently told you was simply not physically achievable in a sustained, stable way. The object was first flagged through data collected by NASA's X-ray observing instruments, which are specifically designed to detect the intense, high-energy radiation produced by matter falling into black holes. Researchers noticed something unusual almost immediately. The X-ray brightness coming from this particular black hole was far higher than its estimated mass should allow, based on the standard relationship astronomers use to connect a black hole's size to how brightly it can shine while feeding within the Eddington limit. Either the black hole was dramatically more massive than initial estimates suggested, or it was feeding at a rate that broke the rules entirely. Follow-up observations, cross-checked using multiple independent methods of estimating the black hole's mass, ruled out the first possibility. The mass estimate held steady, which left researchers with the second, far more uncomfortable conclusion. Now stop and sit with what that actually means, because it is easy to let a number like 40 times the limit pass by without absorbing the weight of it. This is not a black hole finding a clever loophole to feed marginally faster than expected. This is an object apparently sustaining a feeding rate that the physics of radiation pressure says should be self-defeating, should blow itself apart before it can maintain that pace for any meaningful length of time. And yet the data shows this rate being sustained, not as a brief spike, but across repeated observation windows stretching over an extended period. Something about this black hole's environment is allowing it to keep eating far faster than physics is supposed to permit. And whatever that something is, it is not currently accounted for in the models astronomers have been using for decades. So, what could actually explain something like this? The leading theory currently being explored involves the shape and structure of the material falling into the black hole, rather than a flaw in the Eddington limit itself. The standard version of the Eddington limit assumes a relatively simple, spherically symmetric flow of infalling matter, radiation pushing outward evenly in all directions against gravity pulling evenly inward from all sides. But real accretion disks are almost never that clean. Some researchers now propose that if the infalling material is structured unevenly, funneled through narrow, dense channels rather than spread out in a uniform sphere, the radiation generated in one direction might not effectively block matter funneling in through a different, less obstructed path. In effect, the black hole may have found a geometric shortcut, feeding through relatively clear channels while radiation pressure vents out somewhere else entirely, allowing significantly more matter to sneak past the theoretical ceiling than a simple, symmetric model would ever predict. It is a plausible explanation. It is also, notably, not a proven one. Simulating this kind of lopsided, channel-fed accretion accurately requires an extraordinary amount of computing power, modeling the complex, turbulent behavior of superheated gas and radiation interacting in 3 dimensions under extreme gravity. And the simulations that exist so far can produce feeding rates somewhat above the standard Eddington limit, but not consistently anywhere near the extreme multiple that this specific black hole appears to be sustaining. There remains a real, uncomfortable gap between what the best current models can produce and what the actual observational data is showing. This is where the story stops being a narrow technical curiosity and becomes something that reaches into one of the biggest unanswered questions about the structure of the entire universe. Because if black holes really are capable of feeding this far beyond the Eddington limit under the right conditions, even occasionally, even briefly, it would fundamentally change how quickly astronomers believe supermassive black holes are capable of forming. Remember the puzzle mentioned earlier, the discovery of enormous, fully formed supermassive black holes existing shockingly early in the universe's history. Black holes that seemingly should not have had enough time to grow that large if they were strictly obeying the standard feeding limit. For years, researchers have proposed a range of possible explanations for this timeline problem. Perhaps the earliest black hole seeds were unusually massive from the very beginning, giving them a head start, or perhaps galaxy mergers in the early universe provided unusually rich, concentrated feeding opportunities that allowed for temporary bursts of accelerated growth. This new discovery adds a third, genuinely compelling possibility to that list. Perhaps sustained, extreme, Eddington-defying feeding episodes like the one just observed are not a bizarre, one-off anomaly, but a real, if rare, physical process that has been quietly helping build the universe's earliest and largest black holes all along, hiding in plain sight because nobody had yet observed a nearby example clear enough to study in this kind of detail. If that turns out to be correct, it would mean that a significant piece of the puzzle explaining how the early universe managed to construct black holes billions of times the mass of our sun within the first billion years of cosmic history has been sitting unrecognized inside a physical process astronomers assumed was essentially forbidden. That is not a minor footnote. That is a genuine missing piece slotting into one of the most stubborn open problems in modern cosmology. And it started with a single object that simply refused to follow the brightness to mass relationship every textbook says it should. Let's talk about the part of this investigation that took the longest and the part that made astronomers initially hesitant to publish anything at all, because a claim this extreme does not get accepted quickly, and it should not. When the first anomalous readings came in, the default assumption inside the research team was not excitement. It was, again, suspicion, the same instinct that governs every extraordinary claim in professional astronomy. Extreme brightness measurements have a long history of turning out to be measurement artifacts, contamination from a foreground object sitting along the same line of sight, or a miscalculated distance that throws off every downstream estimate of mass and luminosity. Ruling out each of those possibilities required an extended, methodical process. Researchers cross-checked the black hole's distance using multiple independent techniques. They examined the surrounding galaxy for any sign of a second overlapping light source that could be artificially inflating the brightness measurement. They repeated the X-ray observations across multiple separate observing windows, spread out over time, specifically to confirm the extreme feeding rate was not a brief, one-time flare that happened to get caught at exactly the wrong or right moment. The signal held up. Every independent check came back consistent with the original startling conclusion. The black hole really is there, really is that far away, really is that faint relative to what its apparent mass and brightness should allow under standard feeding rules, and really has been sustaining this extreme accretion rate across a meaningfully long stretch of observed time. That consistency, checked and rechecked before anything reached publication, is exactly why this finding is now being taken seriously by the broader astrophysics community rather than dismissed as an instrumental fluke, the way similarly extreme claims sometimes are. It is worth pausing here to appreciate just how much quiet, unglamorous verification work sits underneath a headline like this one. Nobody gets to simply announce that a fundamental physical limit has been broken. Every alternative explanation has to be exhausted first, methodically, patiently, the same instinct for skepticism that protects the entire field from chasing false signals. The researchers behind this discovery spent far more time trying to prove themselves wrong than they spent celebrating being right. And that is precisely the process that gives a finding like this its weight once it finally does hold up. So where does this leave our understanding of black hole physics right now? In the middle of an era when new X-ray and infrared instruments keep finding objects that quietly break rules astronomers assumed were settled decades ago? The honest answer, again, is that nobody currently has a fully worked out explanation, and the researchers involved have been direct about that uncertainty rather than overselling a tidy resolution. The geometric funneling theory remains the most promising lead, but it is a lead, not a confirmed mechanism. Some researchers have floated the possibility that this particular black hole may be caught in an unusually short-lived, unstable feeding episode. something that cannot be sustained indefinitely and will eventually settle back down toward standard Eddington limited behavior once the current supply of nearby material runs out. Others suspect that extreme feeding episodes like this one may turn out to be a genuinely common, recurring phase in the life cycle of actively growing black holes, one that has simply gone unnoticed until instruments sensitive enough to catch it in the act finally came online. Distinguishing between these possibilities will require finding more examples, more black holes caught in the same extreme state, and comparing how long each one sustains the behavior before either continuing, stabilizing, or shutting down entirely. That search is already underway. Now that researchers know specifically what signature to look for, the mismatch between measured brightness and estimated mass, existing archival data from previous X-ray surveys, is being systematically re-examined for other candidates that may have been overlooked or dismissed as measurement error before anyone had a framework for taking them seriously. Every additional confirmed example adds another data point to a picture that right now remains fundamentally incomplete. And every one of those data points has the potential to reshape how astronomers explain one of the biggest unresolved puzzles in the study of the early universe. This is what a genuine crack in an established physical model actually looks like from the inside. Not a dramatic overturning of everything we thought we knew, delivered with total confidence in a single announcement, but a stubborn, well-verified anomaly that refuses to fit inside the existing rulebook, forcing careful, patient scientists to admit that a boundary they trusted for over a century may not be as absolute as it seemed. The Eddington limit is not being thrown out, but it is, for the first time in a long time, genuinely being questioned in a way the data itself is forcing rather than theory alone. If this is the kind of story you come here for, subscribe right now and turn on notifications, because we are going deeper into the discoveries that are quietly rewriting the rules of physics next. Drop a comment below telling me what part of this surprised you most, and share it with someone who still thinks black hole physics was settled science. Because right now, 900 million light years away, there is an object feeding on matter 40 times faster than physics says it should be able to, and the people trying to explain how are only just getting started.